I guess, but like no. Oh my god, I shot on paper cut. What am I like 8 years old? I have not got a paper cut since like elementary school, bro.
I don't believe that.
Don't get paper cuts ever.
I don't believe-
Like rip out. Get paper cuts though. I think it's because I never use paper anymore. Like I put like into my mail bag.
Trader Joe's apple cracker box.
This is what happened last night.
I slid my fingers around the edge to like
Learned our lesson.
As soon as it grows back.
Oh, I mean, I'm sure I've gotten one like with it, like, but it's been a long time, like it was an exaggeration, however. I cannot remember. Oh, these are old.
Yeah.
And also I was doing so much architecture yourself. Thank you.
Take another.
You try something. I was
Once you register, it'll just. I can tell you. I might, probably won't get into this.
Dude. The other chicken bacon you give me, that with ranch was way better. Dude, try it. Try ranch, you have chicken bacon, ranch, there's bacon in them. It feels like separated from the
Well, Caesar's in the. That's
Dude, I
what
know.
Try ranch.
Seriously.
Ranch was lit. It really changed it for me.
I like.
I also had it with a fork and knife though.
There's.
I usually do.
It's so soft.
I've never, should I put in the oven?
Right.
There's.
I'm having my Costco pizza tonight.
Funny.
The good one, not like, food court,
You put your towel on, it's like all.
Of course, I read directions.
My method is you towel, all you have is upside down, 1.5 minutes, right?
I
Let
did,
it, I don't know, 30 seconds.
no, mine shot me things.
So that's my method. I'm like, every time I do it, I change my method. It's like a slide. So I control the variable and then I switch out that variable.
Unless I label.
When I just.
It's like,
I thought there'd be more. Okay, so I read one article. The worst machine goes to death. Yeah. I was like, so I couldn't really tell. I was like, okay, so what evidence do we have? Because I don't want to make stuff up, but. I was like, maybe, I just made sure that it's fine. I was like. You're gonna pick this side. Yeah. Like, the middle one is like the last. And then I wrote about that. Yeah, so the only one that has to do is like hair. I like wrote anything that I could think of that I could really. They were like, no problem. Yeah. Yeah, that's why I giggled. I looked up online, I was like, really straight to the goal. Like, What do you think like the?
Do it on Saturdays.
Yeah.
Oh, right. You do always love that.
Yeah.
Yeah.
He's a good boy, but I don't know where.
Well, it's different when they.
So these signs.
When you're going.
No, it isn't. I just want to.
So like. 198. 198. Like.
I have like
That's really good, I think. Did you get a mail-in ballot? Did you look? When you did that, was it like paper stamp?
Yeah, I had paper stamp.
I was paid. Because here's the thing, you just have to pay for stamps. I know one time where. Well, no, I didn't have to, I don't have to for like my actual ballot. I have to to request. Oh, that's weird. For the actual ballot, they give you like the info and it has to get printed off. But
Yeah.
For my request one, I had to go get a stamp. It was
That was
such a-
terrible. Weird. I just.
It was like the worst era.
That's why I was asking, because apparently my roommate who's from Connecticut has to like paper stamp to mail her mail-in ballot back to her part of Connecticut, but I don't have to pay for it. But I was like,
We're passing a law, we're trying to pass a law in Connecticut to change that.
you shouldn't have to pay to vote.
yeah.
That's a part of the, I think that's a part of the absentee balloting for
Yeah.
Connecticut now. So if we pass this to have it subsidized.
One of the things that goes on for Massachusetts is to whether or not you can legally grow fruits, which is pretty great, actually.
Just grow them, not and take them as well.
No, I think it's like intake too. It's like, hold on, let me
Okay.
pull it up. It's in here, the list of things.
Let's not get me started on All right.
Yeah, it says psychedelics, like. it's kind of-
Okay, guys. Hi, everybody. I want to finish up phases today. I just got a little bit of chat to do about phases and allow us to kind of transition into equilibrium, which will be our second to last topic. We'll talk about equilibrium for a couple weeks. Chemical equilibrium. We'll look at a very specific case study in chemical equilibrium, a very famous one, starting next week. I just want to finish up a little bit of phases to kind of set our stage for equilibrium. Homework 4 has been posted today. It's due next Friday. It's a little shorter than usual. It's a lot of some Excel, mostly Excel actually. Not too bad. Less math. There's some math. But it's mostly on phase tree. It's all on phase transitions. And the next homework set will be, we'll have 2 more homework sets. One will be on equilibrium. And then the final one will be the final of the class. Oh, no, sorry, we'll have one on equilibrium, one on kinetics, and then we'll have a final that kind of puts everything together. All right. So I just want to talk today about one more example I introduced very quickly at the end of class last time. I didn't really give it a chance to marinate with you guys. So I want to talk about it today because I think it's very, very interesting. What we've seen so far, kind of what the brunt of my discussion yesterday, last class was that there are kind of 2 different types of phase transitions. And they kind of fall into 2 different classes. Again, the difference between solid to liquid and liquid to gas are very different. They are different arrangements of the material. Chemically, they look very different, right? Melting is very different than vaporization. But in terms of thermodynamics, they're very much the same. Bless you. And there's a bunch of different ways that physicists and chemists have annotated these classes. And over the last 100 years or so, we still kind of put things into 2 categories. Those 2 categories have become more amorphous and nebulous and less explicit than they used to be in, say, the 40s and the 50s. But we generally still put these things into 2 classes, and we've learned there turns out to be exceptions. There are things that don't really quite fit into the 2 categories, kind of like edge cases. There's types of weird phase transitions that appear. But by and large, they kind of fall into these 2 categories, at least for chemistry. One, of course, is what's called a first order phase transition. This is the new first time I've ever used these terms. And this is melting, freezing, vaporization, sublimation, etc. Right, and the thing that distinguishes these phase transitions from all other ones is that these absorb or emit heat upon transition. Right, we saw that in vaporization, right? You heat the water up, you heat your liquid water up to 300 to boiling, right? So it's at boiling, it spontaneously starts to boil, but you still have to have enough heat energy in your system to put in that 40 kilojoules of mole you need to vaporize, right? You have a delta H of vaporization, right? You have to put in a positive amount of heat into the system to get it to boil. Right, so it doesn't just like, it doesn't take, it always has a cost, if you will, an enthalpic cost. Likewise, the opposite direction, if you take gas and put in the liquid, the system has to emit that heat to liquefy. Right, so there is some change in H, if you will. And there's probably also some change in entropy as well across the phase transition. Right, I want to look just very carefully at this, kind of from an empirical point of view. That's the wrong thing. We were to, for instance, plot as a function of temperature our different parameters of our system. Right? So for instance, let's plot H. Right, and then we'll say that, for instance, the system, we're heating it or something like that. This is the transition point, the transition temperature, right? So let's say we're melting, for instance, this is liquid and gas or something like that. And the enthalpy, of course, increases slightly as a function of temperature because of the heat capacity. But when we hit that melting point, the enthalpy has to spontaneously jump up to a higher level, right? Because there's going to be, for water, 40 kilojoules a mole difference at the boiling temperature between liquid and gas. Right? So the enthalpy of the gas appears out of the phase transition at a different point. Right? There's this discontinuity, if you will. And this is delta H of the phase transition. Right? So H is discontinuous at the transition temperature. Right? And that means that, right? Imagine you have gas here and liquid here. Right? And we're cooling, right? We're cooling a gas and condensing it into a liquid. Right? The heat of the gas decreases as a function of temperature because of its heat capacity. And then you hit the phase transition point, right, where it wants to condense now. In order to do that, it needs to release 40 kilojoules a mole of heat for water. And so suddenly when the system ends up on the other side of the phase transition, its heat is now dramatically lower by that difference. Right? So it's not a continuous function, it's a discontinuous function. And so H doesn't just move smoothly. Heat doesn't move smoothly through the transition. There's a discontinuous jump because you're going from two different materials of two different organizationals, right? They're two different organizations, gas and liquid. And there's a distinct amount of energy you need to put in to kind of mix up that, right? Break all the intermolecular bonds in the liquid and start to mix things up, right? That's a delta H. Now, what about the heat capacity? Right? What does the heat capacity look like across this transition point? We plot the heat capacity versus the temperature. All right, and again, let's assume liquid on the left, gas on the right, we're boiling. And what happens to the heat capacity of the liquid as we start to approach the limit, as we start to approach the vaporization temperature, the boiling temperature? What happens to it? Well, let's start at low temperature, right? You put your water on the stove. You apply a fixed amount of heat with your stove coil, your heater. into that, right? And so the temperature is slowly going to increase on your hot plate at some rate, which is proportional to the heat capacity of the liquid. And what you actually notice is that as you start to approach the boiling temperature, right, it's really easy to test this with a thermometer and a thing of water, right? If you watch the temperature, not a thing of water and a thermometer, sorry. If you watch the temperature of your liquid as it approaches 212 Fahrenheit boiling, your water, you find that as you start to get closer and closer to 212, the temperature increase starts to roll off. So it gets closer and closer to 212, and then suddenly it starts to boil and the temperature doesn't change anymore. Right? It's easy. Go measure this. Go put a thermometer if you have one that's high enough to measure 100 C. Put it in your water. You boil the bejesus out of that water, constantly putting energy into it, and the temperature never changes, right? It's always at 100 C. That's the whole point of boiling, right? It doesn't increase the temperature of the water. All of the energy at the boiling point, all of the energy you're putting into the water from the coil, from your stove, is being put into that phase transition. So all the energy you're applying to the system is being used to circumvent this delta H, right? So once the system gets here, 100% of the energy coming from the stove is getting put into this transition here. Okay, so what happens is at the phase transition, the system starts to boil, and then the temperature stops as the energy is starting to feed into the system still, right? That you never turn the stove off. The system stops heating because it's boiling, doesn't heat anymore. So what that leads to is a heat capacity that diverges. So the heat capacity goes to infinity as you approach the limit. Goes to infinity. Right? Because again, go try it. It's very hard to heat boiling water above its boiling point because all that energy is going to be used to boil. So the heat capacity goes to infinity. And then on the other end, right, you have now a gas. Again, if you liquefy a gas, you see the same thing. When you liquefy a gas and you want to cool it, imagine the opposite of a heating gun. You have a cooling gun, a refrigerator. Refrigerator's pumping energy or pulling energy out of the system to liquefy the gas. And as that gas gets closer and closer to the freezing, the liquefying point, we call it condensation temperature, coming this way, all of that energy all of the refrigeration, all the energy used by the refrigerator to pull that heat out of your material is being used to do this delta H jump. Right? It's the opposite. Right? So the heat capacity on the other side also diverges. And the heat capacity of the gas, of course, is lower than it is for the liquid, so it drops a little lower. Okay. So 100% of applied heat energy is used to drive the phase transition. Right? That's why it diverges. Okay, we can look at other parameters, right? We can look at volume, we can look at enthalpy, right? And it should be pretty straightforward, right? Let's look at volume really quickly, right? Density just really quickly, just to show you that it makes a lot of sense, right? T in molar volume. Again, I'll put my melting point here. Right, and if the liquid, of course, is dense, right, that means that you need a very small amount of volume to put a mole in. So the molar volume of liquid, it's not very compressible. It doesn't move very much, right? So it kind of looks like a flat line. Right, and then the system boils. We've now replaced it with a gas that has much higher molar volume, right? Because it's much less dense. And it also is much more compressible. So as you increase T, right, the gas gets less and less dense, right? So it wants to push out. So you'll have something that looks kind of like this. Right, and of course, there's a distinct discontinuity in the change in the molar volume, because you have to go from a dense, why is that not updating? Sorry, that's not weird. Let me share my screen one time. So it's updating on my screen, but not on here. Oh, I got logged out. Sorry. I got kicked out of Zoom. That's a new event. Ooh, this is slow. I bet you I know why it's slow. I got something running in the background. Okay, sorry, guys. Okay, share screen. Okay, sorry about that. Okay, yeah, so again, you have a liquid on this side. It's not very compressible, right? So as temperature increases, the density of the material, the volume of the material doesn't change much. It's kind of flat. And then, of course, the gas, of course, is freely compressible. Right? That's the advantage of the gas. It could be basically any volume it wants to be. It's not too hard to make it. But of course, there's a distinct difference between the volume of a gas and the volume of a liquid. So there's a discontinuity here as well. Okay, so that's basically all first order phase transitions look like this, right? How big this discontinuity is, right? The values of where the curves are, if you will, and where the intercepts are. And everything changes as a function of material, right? Some materials have bigger heat capacities, more delta H, less delta H than others. But in terms of their graphical behavior, right? How these parameters behave as you approach the transition point are all the same. Totally equivalent. Okay. Delta H and delta V, for instance, and delta S, they have these discontinuities in the curve where there's a distinct change in those parameters between the two phases. And that corresponds to a diverging heat capacity at that temperature as well.
Can I ask a question?
Yes, ma'am.
So, first I just want to clarify, the dotted like T line, they're also at the same temperature, right? You're saying at the
Yes,
transition.
these are the same plots for three different things.
And also, are these only true like in this way if it's like liquid to gas?
No, it's solid to liquid, solid to gas would be the same thing.
How come for the density one? Because I felt like you were saying because liquid can't be like compressed very easily, but
Right.
gas can. So if you're
Right.
going from gas or
Right, so that the compressibility would be the derivative of volume with respect to temperature. So the compressibility of the material has to do with the slope of these curves.
yeah.
And we'll talk actually on problem set 4, we talk about compressibility. But the idea is that a liquid's not very compressible, right? So as you change temperature, its density doesn't change very much.
Mhm.
So this is relatively a flat curve like this.
So what about if you were going from solid to liquid though?
Well, solid would also be flat because it's even less compressible, right? For a solid, it would basically be like this.
And then on the other side, it would be less.
It would be less, that's right.
Okay.
Exactly.
Yeah.
All right, we'll look at compressibility of diamond and graphite on this problem set. We'll talk about that a little bit. About why you don't really, one of the assumptions that we make in chemistry is that liquids and solids, they don't compress. Right, they fill a volume that's largely pressure and temperature independent. And I have you guys look kind of at that approximation in problem set 4. Okay. So these are all the transitions that you know and love or fear or don't care about, whatever you want to feel, however you want to feel about them. But there's another class of transitions called second order transitions. And these are these critical transitions, the things where you have critical points. All right, these are things like, as we'll see, magnetism, liquid gas critical temperature, criticality. An alloy, a binary mixture, separating. Et cetera, et cetera. There's a bunch of different ones. All right, this is kind of an amorphous group of phase transitions. Basically, everything that's not a melting type process gets fall into the second category. And these are all very different things, right? Magnetism, the criticality of liquid to gas, the supercritical at the critical point. Homework 3 is all about binary mixtures, right? You saw something about a critical temperature there where the system spontaneously separates into 2 phases, 2 layers, and a binary mixture, right? These are all second order phase transitions. And what does a second order phase transition look like empirically? Well, the interesting thing is that these absorb or emit no heat. So delta H, which is equal to delta S, is equal to 0 at these transition points. So these are transitions that rearrange the material into a new arrangement, a new physical arrangement. Or if something turns on, like a system going from not magnetic to magnetic, we'll look at that in just a minute. These processes happen without any heat exchange. Basically, the idea is that there are perhaps 2 different arrangements of the system, and one is more energetically favorable than the other. And then as you start to approach the critical temperature, those 2 possibilities become the same energy. And then, for instance, in liquid and gas criticality, that would be, for instance, the 2 choices. So below the critical point, the stable arrangement is to have 2 layers, a gas and a liquid. And so that's very stabilizing, right? And then as you start to approach the critical point, the energetic favorability between having a liquid gas 2-layer system and a fluid 1-layer system becomes equal. So at the critical point, the energy difference between having 1 fluid and having 2 fluids that are separated, a liquid and a gas, becomes indistinguishable. They're the same energy. And as you go above that critical temperature, the 1 fluid arrangement becomes more stable. Okay, so what you have are these 2 arrangements that are competing in terms of energy. And at that critical temperature, they're equal in energy. They're equally likely. When you go past it, the 1 fluid system is more stable. It's lower energy. So the system just kind of smoothly moves from one to the other. Smooth is a bad word to use here, but it looks comparatively much more smooth. So let me show you what these curves look like now. So again, we have some critical temperature where the system transitions between two phases. And the idea is that across this barrier, H does not change. So let's imagine, for instance, H is looking like this here. All right, it hits this point right there. And what actually happens is that because there's no enthalpy change, there's no discontinuity. So on the other side, it approaches that point, but it has slightly different curvature. Something like this. Right? So here you have, this is continuous, but not smooth. You see how I've made a little cusp there, right? So the liquid, you can imagine this is liquid plus gas, if you will. So in a like carbon dioxide, you could say this is the liquid plus gas, and this is supercritical. And what happens is as you approach that temperature, your enthalpy, again, you're putting more heat into the system. And then the system now spontaneously rearranges to some new orientation, right? Which is that supercritical fluid. It's 1 phase, it's 1 layer, no coexistence anymore. And that has a different curvature, a different derivative, if you will, of H. So it looks slightly different, but they meet at the same point, right? So delta H is 0, but it's not smooth. What this means is that, in fact, the second derivative of energy experiences a discontinuity. All right, so if we were to take the second derivative of H with respect to temperature, which is the derivative of enthalpy with respect, sorry. So let me stop over. dH dt. Right, the first derivative of enthalpy with respect to temperature is the heat capacity. The heat capacities match at this point And then you need to take the second derivative, which would be the derivative of heat capacity with respect to temperature. That's called thermal expansion. And the thermal expansion experiences a discontinuity. Basically, the liquid and the gas expand differently at a different temperature, how they spread, if you will, than the fluid does. Right? So some kind of derived property experiences a discontinuity like heat, but there's no discontinuity in the heat. Right, so the parameters, if you will, the extensive parameters of the system change suddenly, but not the intensive parameters. And just very quickly, we'll look at heat capacity here. Heat capacity also does not diverge. Let me clean it up a little bit. But it does experience a discontinuity. Or sorry, a discontinuity in the derivative. That. And then the volumes. Sorry, this should be T. And this is V. Volume is the derivative of energy with respect to pressure, right? Gives energy with respect to pressure is molar volume. Molar gives energies like enthalpy is continuous at the transition point, so its derivative is also continuous. But it has kind of a funky shape. Something like that. Not smooth. Okay, so the idea is that the function exists at the transition point, right? It's smooth and continuous to the transition point, but the derivative does not exist at these points, right? If you notice, the derivative doesn't exist here. So the derivative here, dCp dt, experiences a discontinuity. Okay, so in first order transitions, the first parameters, the intensive parameters, heat, volume, right? These are, sorry, the extensive parameters, heat, volume, heat capacity, right? These are discontinuous. They experience a jump at first order phase transitions because it releases heat. In a second order phase transition, again, something has to change, right? Because you're rearranging the system. So some property of the system must be different across the two. But in a second order phase transition, the main extensive parameters, heat capacity, volume, enthalpy, entropy, they're continuous in that both phases meet at the same point, but they have different behaviors, okay? Different derivatives. Their derivatives are not continuous.
Can I ask another question?
Yes, go
Is
ahead.
it the first or the second derivative?
There's a second derivative of energy. Second derivative of energy.
But the first, I'm confused though, because it's the first derivative of the, when you're talking about the heat capacity.
Oh, yeah, so the derivative. Right, so this is the first derivative. Okay, so great question. So heat capacity is the first derivative of heat. And it's still continuous, but the derivative of heat capacity is discontinuous.
Okay, that
So,
makes sense.
right, the derivative of heat capacity is the second derivative of energy. So that in a first order phase transition, the first derivative experiences a discontinuity. In a second order, the second derivative does. So that would be the derivative of heat capacity, not just the heat capacity. All right, these are just small points. I'm just kind of just showing you the distinct difference about it. I think there's a more interesting way to explore this idea graphically. All right, let me just show you what it looks like, the results of this. And I kind of mentioned this before last class, I'm going to mention it again. There are two consequences of these results. One is that first order transitions occur locally. And here's an example of that, right? Freezing. Into a crystal, like ice, requires nucleation. right? What does that mean? Well, that means that, imagine you've taken a glass of water. It's very hard to do in normal settings, but you can set it up and experiment with this. Take a glass of water, very, very pure water, and a really, really clean cup and a really clean environment, right? No dust, no dirt, no scratches on the glass, like just beautiful glassware, nice and clean water. And you put it in a refrigerator, a really powerful refrigerator, and suck the heat out of it really fast. Okay, you want to do this in dry conditions. You don't want any aerosols, you don't want any dust particles, nothing. It's a perfectly clean environment. You cool that liquid down. You can cool that liquid down below its freezing point. Call it super cool. Right? You can super cool a liquid below its freezing point. You pull it out of the system, and pull it out of the cooler, and you just have liquid water. You put a thermometer in it. Hopefully, it doesn't nucleate on the thermometer. You pull a thermometer in it, it's going to read below 32 Celsius or 0 C, 32 Fahrenheit. And you can get this to nucleate and freeze immediately by taking a glass stir rod and scratching a little micro abrasion on the side of the glass of the wall on the flask. And so what you do is you make a little glass particle that floats in the water, and that little material is used as a nucleus to fill that, to make that crystal form. Right, so the water doesn't immediately freeze. But the idea is that you have this cold liquid. So let's say this is water below 0 C. And I put a little piece of glass in there, a little piece of crap, called a nucleus. And what happens is that the water locally around that nucleus starts to freeze. Right? It uses the nucleus as a point, if you will, a surface for the crystal to grow on. Right? So what happens is that the crystal will start to grow. So this is ice crystal. And then as the system commences over time, right, the entire thing will start to freeze out. So the freezing propagates. Right? And eventually over time, the whole thing freezes out, right? But it doesn't happen simultaneously. The whole liquid doesn't spontaneously freeze, right? It starts at one point and works its way out. You can watch this on your, an ice tray, right? You put an ice tray in the freezer, which I do every day because I'm obsessed with ice. And you go, put it in for a couple hours and you pull the ice tray out and it's not completely frozen. You've got a little ball of ice, but the rest of the liquid in the tray hasn't completely frozen yet, right? And that's the exact same thing, right? The water, even though it's one system, it takes time because the freezing propagates from a starting position and diffuses out through the rest of the liquid, and that takes some time. All right, boiling's the same way, right? When you boil the water, it's not like the whole thing just magically just becomes gas, right? You have to pump heat into it. You get little bubbles of air pockets of water. Sometimes you have regions of your liquid that boil faster than other regions, right? Boiling's not always equal. Right? It's the same concept. Things that happen locally. Second order transitions, however, occur globally, which means that the entire system transitions simultaneously. So if you have, for instance, a flask that has some liquid and some gas, and this is at T less than Tc, you have liquid and gas, and you heat above Tc, sorry, heat 2, T equals Tc. And suddenly what you find is that the entire system is now just one fluid. Doesn't take any time. It happens without any drama. you have one phase, this is T greater than Tc. One fluid phase. All right, and this happens simultaneously. Okay. Below Tc, you've got this coexistence. We kind of saw this in that video of that mixture free separating and coming back together. Suddenly, when as you approach T equals Tc, the entire system becomes opaque at the critical point, and then it all clarifies above the critical point. You just have one clear phase. Right, the whole thing transitions simultaneously. All right, not only that, but you can show, we won't show in this class, at T equals Tc, the correlation length which is the length scale at which some molecule in the system, some particle loses knowledge of the other ones. All right, so imagine that we have like in here, in the flask, we mark a little molecule here in the bottom right, say, hey, this is molecule A. Does it know anything that molecule B, which is way up here, is doing? Right. And so in this case, the low T minus equals Tc. If I pick a little molecule in the bottom and I ask, do you know anything what's going on up here? Of course, it's going to say no, right? Because we have this little thing buried in the liquid. We have a molecule way up here in the gas. They're different in great environments, far apart, right? This molecule up here is not going to influence the one down here. But what happens at T equals Tc is that the length at which this molecule down here stops to know the other ones. Okay. Again, let me go back a second. At less than Tc, again, you can think that this molecule right here in the bottom right corner of the flask knows something about the motion of the molecules nearby. But as you start to go further and further away, it's less and less influenced by the molecules far away. Because the gas is moving randomly, it doesn't really affect the liquid. But as you start to approach T equals Tc and the system transitions from two phases into one phase, what you actually find is that this length scale, which is how long on average does information about one molecule lose information about others, that length diverges. It goes to infinity. And what that means is that every molecule in your system knows what every other molecule is doing. It doesn't matter what size it is. It could be the size of this floor, right? If we had a two-dimensional fluid in here, what if this was a giant vacuum chamber that we filled with CO2 or some material that we brought to a critical point, and we asked the question, do the molecules in this corner know anything about the molecules in that corner? Below Tc, no, they don't. In fact, it exponentially decreases as a function of distance. But as you start to approach Tc, what these molecules over here are doing in this corner dramatically influence the ones that are doing behind Kayla in the back. In fact, it diverges to infinity. So I can take this entire room and stretch it out across the United States of America, across the Earth, across the solar system, and transition the entire system across the critical point. The molecules on Mercury know what the molecules on Pluto are doing, by definition. So this length goes to infinity. This length scale goes to infinity as T goes to Tc. So in a second order phase transition, everything happens simultaneously and globally. The whole system transitions into a new phase simultaneously. Very, very interesting. And it's not surprising that traffic jams can be modeled by second order phase transitions. They also appear spontaneously, and as you approach the critical temperature, as I've explained before, traffic problems way down the road start to propagate towards you a mile down the road as the density gets closer and closer to that critical density. So let me show you an example of this. I think it's easier just to see it. So let me just explain very simply what this example is. Just a 2-minute explanation. It's called the icing model. And the idea is that we're going to build a little magnet, a 2-dimensional magnet, on a grid. All right, so we're gonna make a 2D material. We call this a 2D crystal or 2D solid. All right, and now each grid point, we're gonna put an atom. I'll just do those for now. Each one we're gonna put an atom. And each atom has one and only one property we care about. All right, each atom. So we'll call this atom I, A sub I. A sub I has only two possibilities, right? In problem set 3, we called it A and B. Here we're gonna say that either A sub I is either plus 1/2 or minus 1/2. And these are what we call up and down. Right, and you can think of these as electrons. Or sorry, atoms. Spin 1/2 atoms. Like electrons. Okay, so electrons are atoms. Like think about an electron and a hydrogen atom. It can be spin up or spin down, right? And each orbital can hold an up or a down. We're going to treat each atom like a spin, right? It's got an up or a down. You call it A or B. It doesn't matter what you call it. And the net magnets, the interesting thing about this is we're going to take this system now. And we're going to say that the energy of this system. Let me just make sure I get it right. The energy of this system is minus the sum over all the atoms of an interaction between two atoms. We'll sum over two atoms. This is a two atoms pairs. There is an interaction between atoms I and atom J. This is an interaction. Term with an energy times A sub I, A sub J. Okay. And we're going to add an additional term, which we're going to turn off. This right here is an external magnetic field. And we're going to assume this is 0. Assume it's 0. Okay, so what this says is that if AI and AJ are neighbors, JIJ takes on some value, some positive value. It's not equal to 0. Okay, so that means they interact. And otherwise it's 0. They're far apart. Are not neighbors. Jij is equal to 0. Okay, this is just like the problem in the homework 3, right? Except now what we're saying is that if let's say atom A is 1/2 and atom B is 1/2, we get a minus J between them. If this is minus 1/2 and this is 1/2, we get a plus J. Right? And we're going to set it to be what's called ferromagnetic. Right? Which means that like spins attract others. Right? This is the opposite. Oh, wait, no, this is the same. Same as homework 3, right? It's the same idea. Right, it's the same idea that A's attract A's and A's repel B's that are nearby. Okay, same idea, except we're just renaming A to be up 1/2 and B to be down, -1/2. Okay, same idea. The only thing is now these are magnets, basically we're forming a magnet with these. And we can apply something that a magnetic field, which causes them maybe to align with the magnet, right? If you put a magnet on top of another magnet, right, the magnet aligns with it and attracts it, right? We're going to turn that off. So this looks a lot like problem set 3. All right, so what we're going to do is we're going to model this system. All right, we're going to give it a temperature, some heat, some available entropy, and we're going to watch this system arrange its spins around at a given temperature and see what the orientation of the system is. Okay, and one of the key things is that to note is that so note if the number of 1/2 particles is equal to the number of -1/2 particles, there's no magnetism. Okay, but if n12 is not equal to n -1/2, meaning there's not a 50-50 distribution, the system is magnetic. Right, the idea is that you want the system to have a north-south direction, a pole, if you will, right? You want it to create a magnetic field, which means it has a north-south pole. Right, so the idea is that you want to have more ups than downs, so the net direction of the magnet is facing up, or vice versa. More minuses than pluses, then the net spin of the system is pointing down. And when a magnet comes in, it would attract to it that way. Okay, so we want to see where the system goes from being not magnetic to magnetic. All right, so let's go look at that. I have a nice formula, nice way to simulate this that I showed you before. Except I closed it. Here it is. Okay. All right, so I'm going to turn up the temperature really high. Now, let me turn, it's a little laggy on the screen here. Okay. Is there a way I can make this go faster? No. Okay. So anyway, it looks much better on my laptop screen than it does on Zoom, but that's okay. So right here, I have a lattice of 64 by 64. Okay, so there's 64 pixels. Each pixel, if you will, is an atom. There's 64 this way and 64 this way. And black and white mean plus and down, minus, up and down. Okay, so this system is set to a very, very high temperature. The critical temperature of the system is around 2.6, I think they calculate. So this is really, really high, right? It's a hot magnet. And what do we see? Well, we see that the system is basically just static, right? Black and white, right? It's just random, right? Minuses and pluses, they're constantly swapping back and forth. The systems are exchanging, the atoms are moving around, they're flipping back and forth. They can't really align to any particular arrangement together because there's so much entropy, there's so much heat, right? That the attractions between each of the pluses and each of the minuses are completely drowned out by the heat, right? So what you have is just static effectively, right? This is what a material that is not magnetic looks like when it's not magnetic, right? Basically all the pluses and the minuses are randomly moving around. A really good example of this is iron, right? Iron is not a permanent magnet. Iron is magnetic, right? If you put a magnet towards a piece of iron, it magnetizes and it connects. But if you just leave a piece of iron out by itself for a long time, it loses that magnetism and is no longer magnetic. Right? So you have to bring in an external field, which would be your fridge magnet, for instance, to get these things to align. And I can show you that to you. Right? What happens if I turn this field on? Right? So now I'll turn on the external magnetic field. Well, I actually might not have enough field here. Let's turn the temperature down a little bit. Right, and so let me change, right? So here you can see now I have turned the field on. I've turned it positive so the whites are attracted to the field. Whites match the magnet. I've put a magnet, right? I've put a fridge magnet right next to the piece of iron right here, that's your fridge. I've turned it down a little bit, right? And you can see it's mostly white now, right? Because the system is being magnetized by the external magnetic field, and the system largely aligns towards it. And you can see here, this is a plot of the magnetism of the system. If this were at 0, there would be no magnetism. You can see it's averaged out a nice value of about 0.5, 0.6, which means this is now magnetic, right? The system is magnetized, right? There's more white than black. Likewise, if I turn the field around, I get the opposite effect. See that magnetism is now switched to negative. It's a negative field, this arrangement. Okay, this is what iron does when you, again, iron's hot. When you're at high temperature, iron is not magnetic. But the moment you bring external magnetic field in, it magnetizes, and you can see what happens to it microscopically here. All right, so let's think about now, let's get rid of the field. Because we understand that magnets work. Right? You guys ever heard that Insane Clown Posse song where they go, magnets, how do they work? We should show them this. So you can see now I turned the field off, and now the field is now averaged to 0. Turn on positive field, negative field, no field, and the thing's randomized. All right, so let's turn the temperature down now. I think TC is 2.26. So let's bring it just a little higher. So we're just a little above it. Now let's watch, right? So now again, we see some variation in the system, right? It's still pretty staticky, but what can you tell, right? You can kind of see that the densities of the clumps, which are still random, are getting much larger. And they tend to oscillate a little more slowly. In fact, you can kind of see it here. It's kind of hard to see right now, but we'll see it more clearly as we get closer to the critical temperature. The magnetism is fluctuating above and below 0. Right, and the idea is that we have these density fluctuations, right? The system spontaneously has these large clumps start to appear that appear for a small amount of time, right? So if I freeze this, let me just step it. Right, you can see that as I step it, the average density of black versus white is pretty constant, but you can see that there are times where maybe there are more black than white or more white than black, right? You can imagine that they're just randomly that can happen. We can count if we really wanted to. But you can see here, right, there's this period right here that I've stepped through where the magnetism is kind of net 0 or net negative, right? That means I've had just an extra few blacks than whites at one time, and then they fluctuated away and now I'm above 0, which means I now have more whites than blacks, right? So what's actually happening as we get closer to critical temperature is the system is now oscillating kind of around the median, right? The average is still 0, but the standard deviation, the variance of the magnetic field, the magnetic moment of the material is starting to vary more, right? It's not going like this now, where it's just averaged around 0 really, really fast. It's starting to go like this. It's going to oscillate more and more slowly. Let's see if that continues. So let's go to 2.7. Restart it. Right, and now watch these fluctuations, right? Look, now there's these big positive swings, negative swings, positive swings, negative swings, right? The wavelength of the fluctuations, in terms of time, the frequency, if you will, the period of the fluctuations are starting to get longer, right? And that's not surprising if you look at it. Look, there's larger, right? On average, there's about 50 black and 50 white. But as you can see, the clumps are starting to clump up more, right? You're getting more fluctuations of these large density clumps of light spins that are all being randomized, right? And so now things are starting to compress together, right? You're starting to form little droplets, if you will, of spins that are transient, right? They don't last a long time, but they're starting to get bigger and bigger and bigger as we get closer and closer to temperature. And that causes larger and larger fluctuations in the magnetic field. Again, the average of the magnetic field is still 0, but the variance is starting to get larger and larger. The variance now is getting bigger. Well, let's just bring it really, really close now. So 2.26. So let's bring it just above 2.32. Right? Now you can see that the fluctuations now are getting even bigger. Right, the wavelength or the frequency of these sine waves of the magnetism are getting longer, right? The system is now staying, okay, I just crashed again. I'm going to bring this up on the other computer, actually. Is it going yet? No?
I have a question.
Yeah, go ahead.
So like,
I don't fully understand though, like why that's happening when you change temperature, like you.
Well, remember, likes are attracted to likes.
Yeah.
Right? So there's some net fixed amount of attraction a like spin has to a like spin. What is that compensated by with temperature? I just lost something. I think my graph, right. Oh, there it is. Remember, so there's two different energies here. There is the repulsion, there's the attraction energy of, say, black to black. There's a repulsion energy of black to white, which are the same and opposite to each other, just like in problem set 3. And then there's the heat, the entropy of the system provided by the heat of the bath. That is a positive entropy that wants to randomize the system, right? Heat just wants to randomize it. So you have this competition now between heat and attractions. What do the attractions want to do? The attractions want to bring things together closer and closer together and clump them together. And the heat wants to spread things apart and make it random, right? So we're looking at that place now where a disordered system, which is heat dominated, is now starting to compete energetically with an ordered system where there are more whites than blacks or more blacks than whites.
That makes sense, thank
Okay.
you.
So what we're actually looking at here is, think about this as a two-phase system. At high temperature, right? Think of this as just like the binary alloy in problem set 3. At high temperature, we have one phase, right? The blacks and the whites are equal mixed. They're randomized. The density, basically, if I take a chunk of the box, this chunk of the box looks exactly the same as this chunk of the box. And what happens down here doesn't affect anything up here. Right? It's all random. Right? This is one phase, right? This is like a gas. Right? It's a gas of two different materials. Right? And so as I cool the system down, the entropy of the heat energy of the system is now getting smaller and smaller and smaller, to the point where the attractions between like spins, the J's, start to dominate. And that causes systems to clump up, and there's not enough heat to randomize them. All right, let me get to the right temperature. How close are we? Oh, at 2.32. Right, so at 2.32, right above the point, right, we're right near the critical point. And as you can see, the system is still have enough heat to randomize, but the density, right, the density here of black, very different than the density of black here, right? They're still random, but you can see now the system is starting to like become heterogeneous, right? It's no longer homogeneous anymore, it's heterogeneous. It's still got some randomness to it, still a little bit of heat controlling the dynamics of this system. But as you can see, if I freeze this in time and I pull a little chunk out of here, it's going to look different than a chunk over here. Right? The system's starting to become heterogeneous. So now let me put it at the critical point. And this system is going to, right, I want to watch, for instance, right, look what the magnetic field's doing. It's not, I mean, eventually it's going to average. If I wait a really, really long time, eventually the system will re-equilibrate to something that has more whites than blacks. It'll become positive, and it'll come back down, become negative, come back up, become negative. As you can see, it's still going down and flattening. What's happening is the wavelengths of that variation are diverging to infinity. Right, so the frequency at which a chunk oscillates between black and white is becoming infinitely long. What that means is that if it's black, it starts to get trapped in the black. Not only that, think about the wavelength of the system, how long, right? This is a wave in time, the frequency, then you can calculate a wavelength in distance. And the idea is that if you think about the wavelength as a length scale of how this system is oscillating, right? So if it's oscillating very fast, the wavelength is very short, that means that the dynamics are very local. The whole thing is just oscillating chaotically, right? And so what's happening down here isn't really affected by what's happening over here. So the whole system oscillates with this high frequency, which means that all the little tiny little chunks of the system, the things of small wavelength size, are oscillating very fast. But now what we have are these slow, deep oscillations that move very, very slowly. What that means is that this system is starting to equilibrate to some value. And because the wavelengths are long, what that means is that a small change here propagates not only very slowly, but it propagates further and further away. And what you can show, not with this class, unfortunately, in fact, I just learned this math over the summer, is that the wavelength, right, this wavelength of the oscillations of the system from minus to positive, which has something to do with the distance of how the system varies randomly, goes to infinity, right? This is the idea of this diverging correlation length. And in a second order phase transition, the things that happen in this corner affect everything that happens in the other corner. All of the molecules are moving in a concerted fashion simultaneously. And the consequence of that is that the thing that you measure, the magnetism of the system, which is otherwise fluctuating above the critical point, right? It's going like this. Those fluctuations get longer and slower and longer and slower. And eventually they become so long that the system either gets trapped up or down. The idea is kind of like this. I'll just draw it on the board. If T is greater than Tc, you type in time versus average magnetism of the system. The system is oscillating rapidly like this. And at T equals to Tc, or right around Tc, the system now oscillates much more slowly. Yes. And then when you get to T equals Tc, you can think of the system as now oscillating up initially at the initial time, and the wavelength is infinite. So it just keeps going on and on forever. And so what do we observe over a long time at critical temperature? Well, we observe a net magnetic temperature, right? The system basically gets trapped in one of its troughs, either the ebb or the flow of the wave, the oscillation. And so the system will now get trapped. And as you can see here, we're right at the critical point. The system's pretty much just all black. I can reset it. This is totally random. Or restart it and look a little different. Right? This system may eventually equilibrate to something more white, maybe more black. I don't know. It's a 50-50 shot. And now let me draw it below the critical temperature. Actually, it looks like it's going to black this time. Now I bring it well below critical temperature. Right now, the system has effectively formed two phases. And eventually, there's so much cold that all the blacks leave and there's only white left because there's dominant white. And what's more stable than white, black? White, white. So the whites convert all the blacks. And now you have a perfectly aligned material. And it has a stable magnetic moment.
I have a question again.
Yes.
So how does that compare to when T equals Tc though? Because doesn't it eventually like flatten out or does it just not go all the way?
Great question. At TC, it's very complicated.
Okay.
It's very hard to define what exactly does a TC. In fact, what TC does is it's an infinite wavelength. The problem about knowing what exactly happens at a critical temperature is hard because things diverge at the critical temperature. There's discontinuities. So it's very hard to stabilize system exactly at the critical point. So what we typically do is we just sweep right by it. So we either heat over it or we heat under it. So what we observe is a change from, so what we observe in experiment is a change from, let me restart it, from this random like behavior, right? We slowly sweep it down. And what we observe is that, the discontinuities start to appear at the phase transition. You can't stabilize the system at that critical point. It's not stable. Remember, it's at a critical point, let me just write this here. At the critical point, and the reason why you can't stabilize things at the critical point is because the second derivative with respect to temperature is equal to 0. Means the system's not stable. Because remember, the second derivative of the energy has to be positive in the equilibrium. It has to be positive. The second derivative of Gibbs energy at the critical point is 0. It's not positive or negative. It's metastable. So you can't ever stabilize something at a critical point. There is a stable minimum higher than a critical point, which is a random mixture of up and down, black and white. And then there's a stable minimum at lower than critical temperature, which is where you have a majority white or majority black, and you have a separation of the two. They don't exchange. So again, so what happens as you cool this system theoretically, right, is you go, right, it gets random, it gets less random. And as you bring it over past the critical point, the heat is now so insignificant that the system basically just decides whether to be spin up or spin down. Right, and this doesn't look like one phase anymore, right? This looks like two phases, right? You have these droplets, if you will, of down, a black, and a white solvent, right? And slowly the black goes away because eventually the attractions between whites and whites are so significant, there's so many of them compared to blacks, the blacks get kind of dominated out after a while. And now we have a permanent magnet. All right, so what this predicts though, is that we can take a piece of iron, which is not magnetic at room temperature by itself, and cool it down to some temperature, and suddenly it becomes spontaneously magnetic. Right, so there's some temperature where iron magically just turns on its magnetism spontaneously. And I'll just show you what that temperature is. It's called the Curie temperature. And the Curie temperature, I'll just show you a couple different Curie temperatures, right? Curie temperature is the temperature above which materials lose their permanent magnetic properties. And the idea again is that in a true magnet, all the magnets, right, all the atoms are aligned like arrows here. That's what we have in a permanent magnet. And of course, what we saw in a random magnet is that you have a random mixture of up and down. So it looks like this instead of like this. And these critical temperatures, different materials have different temperatures. So here's some examples. And so iron, for instance, is about 1,000 Kelvin. But there's a couple of interesting ones that, like neodymium, for instance, right? Neodymium magnets are really strong magnets that you can buy, like curiously strong ones, the little ones you can buy from nerd stores. They're also the magnets that are used in headphones, neodymium magnets. Right? They're really, really useful because they have a TC right above room temperature, so they're really useful for room temperature permanent magnetism. And then there's all sorts of different types. There's also a different type of magnetism called superconductivity, which is similar to magnetism in terms of it's a second order phase transition of the system. And superconductors, which are conducting materials that have no resistance, so they can freely conduct electrons. They tend to have Curie temperatures around 50 Kelvin. So superconductivity is a very, very hard thing to get. You have to freeze your liquid, your systems down really, really low to get it to conduct, to be a superconductor. But iron will become a permanent magnet at regular temperatures as well.
Can I ask another question? I'm
Yeah,
sorry.
sorry, go ahead, please.
So like, you're saying it's greater than that temperature it's gonna be?
Yeah, so basically, if you take any of these metals and you heat them above this, they'll never magnetize.
They'll never
They'll
magnetize.
never magnetize.
Okay, that's okay.
Never magnetize. The idea is again, think of, again, that magnetism is a two-phase system where you have more of one spin than the other. Right? And above that critical temperature, the Curie temperature, you have one phase where it's 50-50, everything's random, therefore no magnetism.
So then what about when you have like completely one phase, like when you go so below that it like ends up taking completely, like where it's
Well,
all,
then that's a permanent magnet.
okay.
That's a magnet that's most capable, built the highest capabilities. In fact, most magnets tend to be more effective at low temperature than high temperature for that reason. Okay. And interesting, so one thing I want to mention kind of at the end here. I wish I could show this to you in 3 dimensions. It's really cool to see this in 3 dimensions. It's much harder to do the icing model in 3D. It's 2D. It has different properties, in fact. In fact, the way that the heat capacity and how the different parameters of the system change as you go over the heat capacity or over the critical temperature, how the enthalpy changes, how the volumes change, the heat capacities change, all these kinds of things, depends on the dimensionality. 3D magnet has slightly different thermodynamic properties to a 2D magnet, which is very interesting. A 4-dimensional magnet has very, very different properties from a 2D or a 3D magnet. You might wonder what a 4D magnet is. Don't worry about that, but there is such a thing. Things with 4 dimensions. So this is a 2-dimensional system, right? It's got 2 dimensions of space and 2 dimensions of properties, right? Plus 1/2 and minus 1/2. A typical magnet, again, is going to be a 3-dimensional space, right? It's a box, a cube, 3 dimensions. And each of the atoms can take many, many different states. It's a very complicated problem. A lot of people have studied these things. Interestingly, you could also think, well, what about on a line? What if I had a line, 1-dimensional, like a linear magnet, like a chain of atoms? Is that permanent? Nice. Imagine if I did this instead. This is a very interesting fact, I think. Just as a side point, let's put it here to finish up the class. If you have a chain of these little balls, so this is a 1-dimensional item, right? This is a 1D icing model. And you may ask the question, all right, does this ever permanently magnetize? Right, so imagine we start it so that it's like this. Right, is there ever a temperature? Is there ever a temperature? We put T equals TC question mark. Where this system spontaneously magnetizes, or all of the atoms are pointing in the same direction, right? Just like the 2D box, right? That's what the 2D box just did. We saw that it was random and then we cooled it down below the critical temperature and everything aligned. Right? So is this also true for a 1-dimensional magnet? The answer is no. This never happens. Never equilibrates. And one of the interesting things about this is that you can never have 1D magnets are impossible to form. It's actually not too hard to show the math of this. I'm never going to make you do it, but interestingly, very, very interestingly, the dimensionality of the system, right? What kind of dimensionalities in space it fills, as well as the parameter space of each of the atoms, changes the properties of the material quite a bit. The fact is that you can get these flat sheets of iron that will magnetize, and of course you can get an iron brick that will magnetize just fine. You will never get a chain of iron atoms, like a long wire, for instance, to magnetize, because it never equilibrates. Never equilibrates. It's impossible. So this is impossible to form. So it's kind of an interesting side effect, right? So something about the transition, the phase transition, if you will, right? It's not universal. It has something to do with the space of the system, right? It has something to do with the parameters, the dimensionality of the system. And when you go deeper into this theory, you find that the dimensionality of the system really determines the behavior of the system. So they all go through second order phase transitions, except for the 1D magnet, which has no phase transition. It's always randomized. It never forms a permanent magnet. But the 2D, the 3D, the 4D, the 5D all have different magnets, all have different behaviors around the critical point. They all transition to kind of the same class, right? They all do simultaneously. You've seen what that looks like. But the way in which they deviate changes, and it has to do with the dimensionality of the system. Whether it's 3-dimensional, 2-dimensional, whether these can be atoms that have multiple spins or just 2 spins. Of course, there are atoms that have spin 1, spin 0, spin 2, lots of different atoms, especially bigger metals. They can have lots of different possibilities for their spins. And those systems have different behaviors around the critical point, but they all tend to do the same thing, right? They all have a critical temperature where they spontaneously magnetize. They all tend to deviate the same ways around the critical point, but in the way in which they deviate changes depending on whether they're 2D, 3D, or 4D. That's very interesting. And there's a whole theory of condensed matter chemistry and physics that studies these things. If you're interested in that kind of stuff, I can certainly recommend some resources if this is an interesting topic. Okay, that's all I have for you today. We'll start equilibrium on Wednesday. we've got a good sense now that this idea of systems flowing from one material to another. So let's kind of formalize that on Wednesday. That'll give us a nice way to do chemical equilibrium. We'll derive the equilibrium constant on Wednesday, and start working with those tools. All right, have a good one.
Well, if it's not the thing, if it's not, there, then. Yeah,